Hello and welcome to an episode of The Central Equilibrium. I'm Eric Kai, the chemical statistician, and I'm pleased to welcome my guest, David Veitch, who will talk about rational versus irrational numbers and countability. David, welcome to The Central Equilibrium.
Thanks for having me, Eric. I'm excited to be here.
Tell us about your professional background.
So I used to work at Bank of America. I was a fixed income trader. Initially, I was a repo trader, which is very short-term fixed income.
Okay.
Then eventually I was a government bond trader. And I really focused on, kind of 2 to 5 year maturity securities.
Okay. And what is your educational background?
So my bachelor's degree is in commerce from Queen's University. And while I was there, I took some, courses in stats and math. And then more recently, I was recently accepted into the Master of Statistics program, which you have done.
That's right.
At the University of Toronto. So I'm doing that this coming year, and I'll be done in about May. So I'm excited for that.
Congratulations. That's wonderful news. Now, tell us about your overall objective for today.
So my objective for today is to kind of talk about the notion of what is a number and what are some different ways of describing what is a number, particularly rational and irrational numbers, what those are. And then we're going to talk about countability. And specifically, are rational numbers countable, which we'll get to later in the episode.
Excellent. Okay. So shall we start by talking about the various kinds of numbers?
Yeah, that sounds like a good idea.
Okay.
So why don't we erase some of this?
I'll erase. Okay.
So when we talk about the various kinds of numbers, we can kind of formalize that definition with different sets of numbers.
Okay.
So a set is a collection of elements.
Yeah.
So when we talk about a set of numbers, it's just a set where each element would be some sort of number. So why don't we start off with the most basic definition, one that you and me learned in like junior kindergarten.
Okay.
So it'd be the natural numbers. So it's represented. Oh, there we go. That's an N. It's represented by an N with kind of an interesting script on the left-hand side.
I think. How is it?
Yeah, that looks better.
Yeah. So it's the normal capital N, but with the two vertical bars on each side.
Yes. Don't ask me why it's two vertical bars, but that's it.
Okay.
So when we think about the natural numbers, we're thinking 1, 2, 3, 4, and so on. Some people include 0 in there. Some people don't.
Right. So I think that's an important point to point out is that for natural numbers, there's disagreement, unfortunately, in the mathematical community about whether or not 0 should be included in the natural numbers. Some people say it's just the positive numbers. Some people say it's 0 and the positive numbers. Okay.
Yeah.
So those are the natural numbers.
So those are the natural numbers. So that's pretty standard.
Yeah.
Going on, so that's the most basic definition. Eventually you get to grade 3 math, right? And you're talking about integers.
Yeah.
So integers being the natural numbers, but including positive and negative numbers.
Right.
So it's like a mirror image of each other, including both sets of elements. So that would be the integers.
Right.
And that's what I guess you use most of the time until you get to maybe high school or university level math, and then you run into some more interesting concepts of what a number is.
Right. Now, is integers, is that Z?
Yes, Z. Yes. With the double bar on the
diagonal.
Exactly.
Yes. Okay. So these are the natural numbers.
Yeah.
Okay. So those are the natural numbers, and then these are the integers.
Yeah.
Okay. So, and I think it's important to point out integers do include 0. Right?
Yes. The integers include 0 for sure. And I'd point out too, it's interesting because all of the little symbols we'll look at, it kind of makes sense. The Z. Why is it Z, right? It turns out there's it was German, and there's a Z in the German.
Okay, so we'll accept this. We'll accept this.
Accept it without proof. Okay. So we'll move on to the rational numbers.
Okay.
So the rational numbers are basically any numbers which can be a fraction of 2 integers. So let's maybe formalize that. So let's have Q. There we go. Okay, Q. It's got a little bar right there.
Okay, yeah.
Okay, so this would be, let's say, the set of all numbers. P over Q, so that's a fraction.
Yeah.
Or we'll say P is in Z. Say Q is in Z. And Q
Right.
Q does not equal 0.
Right. Sorry, I think this is just a little too small.
Sorry.
If you could write those just a little bit bigger.
Okay, let's write that a little bit bigger then. There you go.
Thank you. Okay. So
there you go.
So the rational numbers are the set of fractions such that the numerator it could be an integer.
Yep.
And the denominator is an integer, but it cannot be 0, which of course we all understand because you can't divide by 0. That's undefined.
Right. Okay. And you can start thinking about the type of numbers that are in the rational numbers. So if P was equal 1, Q is equal to 1/2.
1/2.
That seems to make sense. Or if P was equal to 2, Q is equal to 1, that's just 2.
Right.
So the rational numbers, they include all of the integers.
Right.
And then they include some more numbers like fractions, because fractions aren't in integers.
Of course.
So
we'll just write these are the. Can you just write these are the rational numbers?
Yeah, I'll write it. Rational. Rational.
Excellent.
Rational numbers. There we go.
Okay. So we have the rational numbers, and of course we take the opposite of that. Those would be the irrational numbers.
Irrational.
What are the irrational numbers?
So, and we'll look at this a little bit more later in the episode.
Yeah.
There are some numbers that you cannot represent as a fraction.
Uh-huh.
So some of these numbers include, as we'll see later, the square root of 2.
Uh-huh.
They also include pi. They also include e.
Yes.
Which is like constant growth. It's related with that.
Yeah.
Another way to think about it is these are numbers that have an infinite decimal representation where there's no repeating decimal and there's no periodicity of the decimal.
Right.
So it doesn't go 1.13131313. You can basically prove that those numbers can be represented by a fraction. So pi, 3.1415, yada yada yada.
Right.
It never repeats. It doesn't repeat itself in a periodic or just a straight up way.
Right. So I think one good example is probably 1/3. Right. We know that this is equal to 0.3333.
Yep.
On and on and on. So even though there is an infinite decimal expansion, I'm sorry, I'm really bad at drawing threes today. This is terrible. Okay. So even though there's an infinite decimal expansion of this number, it repeats.
Yes.
So this is still a rational number.
Yes, right? That is correct.
Or if I believe 1/7 is equal to 0.142857, and then it just repeats like this, 142857.
Yes.
It keeps going like that. So even though this is an infinite decimal expansion, there is. Would this be a period? Is this the period?
It periodically repeats itself, right?
Okay.
And the proof actually is pretty simple. You basically look at 1/7. Let's call it. Do you mind if I?
Go ahead.
So let's say a equals 1/7. Do you mind if we just erase that part right there?
Okay.
So equals, let's say 0.14 2857 7, and then it repeats itself. So 157. Repeating, and it's actually kind of interesting what you can do. What you can do is say, okay, well, if I multiply this number, so it'd be, let's like move the decimal, so it's 10, 100, 1,000, 10,000, 100,000, a million. So if I do, let's say, I just 1, 2, 6. And I take a million A. I'm going to subtract A from it. And then you see what you have. You have this part of the number, but then you've lost the repeating decimal. So you get something along the line of 14285. All of a sudden, so this is 900. 999,999.
Yeah.
A equals 142857, and then you can just finish it off saying, A equals 1 4.
And we'll just write a comment.
Oh, yeah, let's put a comment just to make it
clear.
Make it clear.
Yeah. Okay. That's really neat. I hadn't thought about that, but that's a really cool way of showing this. Okay.
Right.
So these are the rational numbers.
These are the rational numbers.
And so sorry. So going back to I don't. Sorry, audience. I took David on a tangent here. Okay. So irrational numbers are numbers that you cannot represent by a fraction of integers.
Right.
Okay.
Yes. And we'll dive into you'd think, and this is part of the reason I find this so interesting. You'd think every number would be able to be represented by a fraction. That just seems to align with our natural understanding of what a number is. But we'll see in a bit that there are some numbers you can just prove this isn't the case.
Okay.
And probably it's worth mentioning the real numbers quickly, because that's what, when you're doing mathematics, usually you're using real numbers, and that is the union of all rational and irrational numbers.
Right. Okay.
So we'll see that later when we talk about bijections and whatnot.
Okay.
That's the real numbers.
Okay. So irrational numbers are numbers that you cannot represent by a fraction of integers.
Yep.
And real numbers are rational numbers or irrational numbers.
Yeah.
The union between those two sets of numbers.
The union between the two sets. Yeah.
Okay. So now shall we now talk about the square root of 2? You mentioned that as an example of an irrational number.
Well, why don't we erase the board quickly?
Okay.
So when you talk about the square root of 2, and the first place I saw this was I took a real analysis class this past year, and it's like the first example you look at in a real analysis class, and it's pretty interesting. What I'm going to do here is use something called proof by contradiction.
Okay.
So I'm going to assume something is true, and then we're going to do some math, we're going to do some very basic operations, and we're going to arrive at a contradiction. So once we arrive at the contradiction, we can now know that what I assumed was true is actually false.
Right, because you're starting with that initial premise.
Yeah.
You use logical deductions to find more and more implications from that initial assumption.
Yeah.
And you arrive at some conclusion that you know is false. And by virtue of just retracing back your steps, if this is false, then that initial assumption must have been false.
Exactly.
Right.
Exactly.
Okay. So we're going to show that the square root of 2 is an irrational number.
Yes.
So we're going to start then. I'm assuming that we'll start with the premise that the square root of 2 is a rational number.
That is correct. Okay. So we'll write square root of 2 equals p over q.
Where p and q are integers. And q cannot be 0.
Q can't be 0. And any fraction, it can be represented in lowest terms. So we're going to say p and q are in lowest terms. Because any fractions have got to be lowest terms. So let me just write that, because that will that'll come in handy.
Okay.
Sorry for my handwriting.
That's all right. That's all right. We understand. We can see this. Okay.
Okay. So square root of 2 equals p over q. So we're now going to do some operations which are pretty logical, nothing controversial.
Yeah.
And we'll arrive at some sort of contradiction.
Okay.
So I'm going to square both sides of the equation.
Okay.
Okay. So I'll just write it out just so it's clear what's going on. So square root of 2 squared equals, let's go p over q.
Okay.
Handwriting's really bad. The square root of 2 squared equals p over q squared. Let's simplify that. So 2 equals p squared.
Sorry, David. Would you mind writing it bigger?
Okay, yeah. Let's write.
I think we can read it, but we just need it to be bigger, just so that it's visible. Good.
Yeah, that's much better.
And just for everybody, that was a q over here. Yeah. Okay.
So we'll multiply each side by q squared. I think that's also reasonable.
Yeah.
Okay.
Okay.
So now let's look at p squared for a second.
Yeah.
So p squared is equal to 2 times q squared.
Yeah.
What we're now going to say is that p must be an even number.
Uh-huh.
So look at this. If you have an even number, you multiply it by itself.
Uh-huh.
It's going to be an even number.
Uh-huh.
If you have an odd number, you multiply it by itself. It's going to be an odd number.
Yes.
So we have 2 times q squared. I don't care what q squared is. I know 2 times it is going to be an even number.
Yeah.
And then this implies p squared is even, therefore p is even.
Ah, okay. Right. So if you have if p squared is an even number,
Yep.
then p has to be an even number. Can you explain that last step? I think I and everybody can understand that 2 times p squared must be an even number, but that last step, why must p be an even number?
Well, you could just look at it by example, right?
Okay.
So what's the product of 2 odd numbers?
It must be an odd number.
Must be an odd number.
Right.
You can find
okay. Yes. Yeah. You know what? Let's actually write this out. I think that's a really good way. So if you have an odd number squared,
yep,
that has to be an odd number. We know this. Okay?
Yes.
That has to be odd. Okay. Now if we have an odd number,
yep,
multiplied by some even number,
that's going to be
has to be even.
Yeah.
Right. Okay. Now, if we have an even number multiplied by some even number,
yeah,
that has to be even.
Yes.
Okay. And if we have an even number multiplied by itself, it must be an even number.
Right. Okay. Because they're both even, right?
Right. Okay. Okay. Yeah. Okay. Yes. Okay. That's clear enough. Okay.
Okay. So I'll maybe write over here that p is even. So. Actually, can I erase the top part, just so we're keeping track of what's going on?
Yeah. Okay.
So we'll use the therefore. Let's go.
P is even.
Okay, p is even. Now, if p is an even number, we have two cases here.
Yeah.
Either p is some odd number times 2, or p is an even number times 2.
Yeah.
So let's take a look at this. So let's say, just as an example, let's say p is 6. Well, that's obviously 2 times 3.
Yeah.
Let's say p is 8. Well, that's the same as 2 times 4.
Yeah.
Okay. So would you agree with me that p being even means that p equals, let's say, 2 times k, and just k is some integer, something like that.
Yeah.
Okay, would you agree with me with that?
Yeah.
Okay. Well, we now have this fact. So why don't let's sub in 2 times k into this part of the equation.
Okay.
So 2 squared equals. We'll simplify it and just expand out what that means. So equals 2. So 4k squared, and we'll do another uncontroversial thing. We'll divide by 2.
Right.
Do you see what the problem is here now?
Okay, so we know that q it has to be an integer. And we assume that the square root of 2 is a rational number.
Right.
Now, okay, so q squared divided by k squared is equal to 2. Now, if I then take the square root of both sides, I'm going to get q over k is equal to the square root of 2. Now, is that a problem? Let me think. Okay, so we know that k is some integer. So we start by assuming that the square root of 2 is a rational number. So I can't quite see the contradiction here. I need your help.
Okay. And you know what? I almost asked you just a little too early, because I think if I wrote this right away, you might have seen it.
Okay.
Q squared equals 2k squared.
Yeah.
Let's use the same logic we used up here.
Okay. So Q must be even.
Yeah. And let's say, I don't know, let's say 2j.
Sure, 2j. Okay.
2j. Okay, originally, the square root of 2, and we ended up erasing it.
Yeah.
We said the square root of 2 can be represented by two integers, p over q.
Right, so this is represented in lowest term. Okay.
Okay, so square root of 2 equals p over q. We picked the lowest terms version of that.
Yeah.
We knew that p's even, q's even. Well, what we have here is equals p over q equals 2k.
Right.
When you look at that, does that look like it's in lowest terms?
No, because you can divide 2 to get k over j.
Exactly. So obviously
you can divide 2 on top and bottom. Excuse me. Yeah.
So we go back to here and we say, wait a sec, this must have been wrong, right? There is no representation. P over q or p and q are integers,
right? Where
they're in lowest terms,
right?
Therefore, square root of 2 is not rational.
Right,
we can't describe it using fractions like this.
Right. Okay. Right. So if a fraction is in lowest terms, is in the lowest term, you cannot divide by some integer on the top and bottom to get it an even a smaller number on the top and bottom to represent the same fraction.
Yeah, it has no. I think the term is no prime common factors. Basically,
okay.
So they don't have any common factors. It's in the lowest terms. Clearly,
right. Clearly, that's not the case. So this right here is a contradiction.
Yeah.
Okay. Okay. So therefore, the square root of 2 is not represented by some fraction p over q, where p and q are integers.
Right.
Okay.
So if it can't be represented by a fraction, remember our definition of what irrational numbers were. Right. Numbers that couldn't be represented by a fraction. Right. It's got to be an irrational number.
Okay. That is a pretty neat proof. Yeah. Thank you for showing this to me. This is pretty cool. Okay. So we've talked about rational numbers and irrational numbers, and we've come up with a pretty neat example to illustrate this.
Yeah.
Let's now talk about countability.
Okay.
So let's talk about the definition of countability first. What is countability?
Okay. So we're going to talk about the definition, but we're going to need to define something else after that in order to understand. So the definition of countability is that there exists a bijection, which we'll learn about shortly, between the natural numbers and whatever set we're talking about. So in this case, we're going to talk about the countability of the rational numbers. Okay. So there's a bijection, so a function between the natural numbers and the rational numbers with some special properties.
Okay. You know what? I think that's an important enough definition that we should write this out. Okay. So a set, say Q, or let's pick some other. A set G.
Yep.
Is countable if there exists a bijection between Did you say the natural numbers?
The natural numbers, yeah.
The natural numbers and the elements of Q. Am I correct?
Or G, as we've described it.
Yes, of G. Okay, so that is the definition of countable. Okay, so now we need to define what a bijection is.
Exactly, because that's what the definition essentially hinges on.
Okay.
So, and we'll write this out. So bijection's got two properties, and we'll go into what each one is. And as the name would suggest, there's two properties.
Yeah.
So the first is it's injective, and this is also referred to as one-to-one. The second is it's surjective, which is, and for anyone who's done French class, this might not surprise them, onto. Onto is kind of the other way of writing that.
So I think it's important to point out that the term bijection applies to functions or mappings.
Right.
Okay.
So it's a function from one set to the other, and if a function has certain properties, we can describe it as injective, surjective, bijective, whatever we want. Yeah.
Okay. So a bijection is a function that is both one-to-one and onto.
Yes.
Right? Okay, so let me write that out. So a function is a bijection if it is both injective also known as one-to-one.
Yep.
And surjective, also known as onto. Okay. So why don't we erase the definition of countable here, and why don't you tell us what one-to-one means?
Okay. So a function is one-to-one if, let's say you have an element in its domain and it maps to some element in its range. It's one-to-one if only one element from the domain maps to each unique element of the range. So in order to maybe formalize this in mathematical terms, why don't I write that out as an equation?
Please do.
Let's say we have a function, and let's say we're going from A to B.
From some set A to some set B.
Yes.
Okay.
So A could be like natural numbers or real numbers or something like that.
Or it could be, say, the set of trucks that are on sale at a certain auto dealer. Okay. Or the set of colors in the rainbow. Okay.
Exactly.
Right.
We won't use colors in the rainbow here.
That's okay.
I don't know the math behind that. But,
that's okay.
Okay. So let's say we have F from A to B. Okay. And let's say we've got let's say X and Y, are elements of A.
Yeah.
So X and Y, they're in A.
Yeah.
Okay. So let's take those and put them into the function. So let's say we have f of x, the function applied to x.
Yeah.
And let's say we know that f of x equals f of y.
Okay.
Okay. If a function is one-to-one, it's defined as when f of x equals f of y, you know for sure, or this implies that x equals y. Or, and some people like this definition a little bit more, or if, let's say, x does not equal y, f of x does not equal f of y.
And could you just write one-to-one on the left here, just to signify that this is the definition of one-to-one? Okay, so we're going to try to articulate this in plain English here. So suppose that this is the image of the function,
Yeah.
So this is the image right here of the image of y of f, the function f.
Yep.
Okay. So suppose that I have these are the elements in the image of f.
Yep.
So you're saying for every element in the image here, it must have come from. So this is the domain.
Yep.
Domain of f.
Yep.
So I think in plain English, what you're saying is, every element of the image of f must have come from one and only one element in the domain of f.
There's a uniqueness to it, right?
Yes,
so there's a unique element kind of in each set. So if you have the function, maps to some element, well, it's only going to go back to one element in the domain.
Right.
It's not going to it's not going to here as well.
Right.
It's not going to there as well.
Right. Okay. Now, I think it's important to point out here that it is entirely possible that some element in the image of f is not mapped by some element.
Oh yeah.
Right. If from it's entirely this could be our function. Actually, we want this to be one to one. Okay. So we want this.
Right.
So here's the domain. And here's the image. Okay, so let's say I have another element here that maps to this.
Yeah.
Okay, but this element here is orphaned. There's no connection between this element and any element here.
Yeah.
This is still a one-to-one function.
Oh yeah, it's still one-to-one.
Right.
Well, look at the definition, right? Like this has nothing really to do with making sure every element in the image has something in the domain related to it.
Right.
It's strictly when you have, an element in the image and you have two elements in the domain. If the element in the image is the same, it's got to be the same element in the domain. That's what it's talking. We're not talking about what you were referring to.
Right. Okay. So that's one to one. Now let's talk about onto.
Okay.
What does onto mean?
And maybe I'll leave that up for 1 sec. So onto means that. And you almost were just referring to this. Yeah. For every element in the image, there's something in the domain that'll map to it. So why don't we formalize that with a definition? So mind if I erase this right here?
Erase whatever you want.
Okay.
Erase whatever you want.
So let's say
an artist must have his or her canvas.
So this is onto.
Yeah.
That's say.
Can you just finish the left side of that O right there?
Let's get that. Oh, okay.
Yeah.
So this will be.
Thank you.
For all, let's say, let's use Z.
Okay.
For example, for all Z in B. There exist some X in A such that f of x, that's a little, f of x equals z.
Okay.
So this is more talking about, we've got the image, the set B, got a lot of elements in it, and for this function to be onto, there must be some sort of element in A that you can put into the function and get B for every single element.
Right. So let's see if I can draw a diagram to illustrate this. I hope that this is okay. So we have. Okay, so this is my domain.
Yep.
Domain of f. Okay, and here is my image. Image of f. Is that legible? Yeah.
Yeah.
Okay. Okay, so it means that for every element in the image must be mapped back to some element in the domain.
Yeah.
Now, it is entirely possible that some element that two elements in the image of F could be mapped to one common element in the domain. If the function is only onto, so let's ignore one-to-one here. Let's ignore one-to-one. If we're just talking about a function that is onto and only onto, it is entirely possible for one element of F to map to two different elements in the image.
Yeah, I don't see why not. Yeah,
right.
It definitely could be.